Okay, so on Wednesday, we showed a very quick exercise to better understand how can we apply the Bernoulli equations. And then the next slide just a very interesting application for the Bernoulli equations. Because I really like to drink the wine, so I understand how the behaviors, as I show in the slide, we call that the decanting. Okay, so the idea is because the wine have the tannin, the inside the wine, but the tannin, a lot of the tannin will affect the tasting of the wine. So usually we need to mix the wine with the air, and then we call that the decanting, 醒酒. And then if you reduce the tannin, and the tasting of the wine will improve. Okay, so the idea, how can we apply the Bernoulli equation for the decanting behavior? So the idea is quite simple, because you can see here there is a small cross-section area, and we call that the small cross-section area will have the high speed. So in here, the red circle in here, the velocity will be increased. And the Bernoulli tells us the idea, the velocity increase and the pressure will decrease. So in here, the pressure will decrease. Okay, at the red circle in here. So you compare to environment. So here is our environment area for the air with a relatively higher pressure, right? With a relatively higher pressure compared to the small hole. So the idea in here, so you have a large pressure gradient. You compare the inside pressure to the outside pressure. So the pressure gradient is large. So in that case, the air can move and flow very quickly going to inside. And then the mix with the air and the wine will speed out. Okay, so that you just speed out the air mixed with the wine. So the decanting behavior will frequently occurred. OK， 所以我们可能你们比较没有看过那个漫画，像我们以前不是会看什么神之九滴吗？然后它里面就会讲这个醒酒的这些原理。那神之九滴里面有讲到那个伯努利的定律，然后他就教你怎么去很快的把酒醒起来。所以我们一般在看电影，他不是在醒酒吗？他拿了酒杯一直在那边磨，就是磨那个摇晃那个酒杯。其实它是增加那个表面的流速，让那个 air， 因为流速变快就会低压嘛。那有低压的环境，那高压的东西就会想要往低压的方向移动嘛。那你的空气的话，对于酒杯来讲，是相对于比较高压的。它可以去促进那个空气去溶解在酒里面，那就可以加速醒酒的这个作用。所以不是在那边演，就是不是在那边假装好像演得很有气质这样子，它实际上是真的要去醒那个酒。我们最近这个那个这个 HDMI 常常有问题，所以那个如果你们平常去 7 买那个200多块的那种红酒，或是几百块的那种红酒，就不用醒了，那直接像啤酒把它喝下去就可以了，因为那个里面没什么单宁。对，单宁要放很好的酒，放很久的这种好酒，它就容易有这种单宁的味道。不过我也是喝不起那种酒，都是喝喉咙优那种低价的那种的，喉咙优还太贵，台啤还比较便宜。哎呀，这个常常都这样子。等一下哦。 我已经带大黑胶来了，你们看我把它定起来了。
我看起来，
它只有一个姿势是可以，
只有一个角度。
就是事实证明我不能讲太多的酒，因为它就醉了。要摇一摇，要把它醒一下。哎呦，哎呦，差点醒来。
看到了。
看到一片曙光。这个我们要再改善这的问题。到时候再接片好了。哎，我想要关掉它的时候，它就好了。Okay, so this is a very interesting idea when we apply the idea in class to the drink wine. Okay, so the table just summarized the two important formula for the Bernoulli equations. The first one we have the head form, and the second one we have the pressure form. So the two formula are the same ideas, but you can depend on what the parameter you have in your questions, and you can apply the different formulas. Okay, so there I just summarize all of the parameter, and the important thing is the units. You need to know the dimensional for each parameters. Okay, so we just have the two exercises, and it will be very helpful to understand the principle of the Bernoulli equation. So the first one, we have the tank, and we actually know the liquid is the water, and we know that the water is almost incompressible, right? So first, we know the water is our liquid material, and we assume the flow is steady flow. And we know that the viscosity effects are not important in our questions. So I emphasize the three flow conditions need to be satisfied for the Bernoulli equations. So the first one is steady flow, right? And the second incompressible flow. And the final one is inviscid flow. Okay, so you have the three conditions to satisfy the Bernoulli equations. Okay, so in that case, we actually know we follow the Bernoulli equation, and I draw the yellow curve is our straight line. And we know that if one straight line and the 2 point will be satisfied the Bernoulli equation idea. So what the idea is we have the pressure at location 1. Okay, the pressure at location 1, and plus the elevation pressures, so gamma Z1, and plus the 2 over rho and the V1 squared should be equal to the P2 plus the gamma Z2 and plus the 2 over rho V2 squared. Okay, because our problems are satisfied the Bernoulli ideas, so that's why we know that the piezometric pressure plus the velocity pressure are always constant. Okay, so that's why we can draw the equation in here. So we have some condition we can summarize. Is the first condition, we know that the P1 should be equal to 0, right? Because the point 1 are exposed on atmosphere environment, so there is no gauge pressure. Okay, and then our target is find the velocity of the liquid in the drain port. So our target is we didn't know the V2. We didn't know the V2, so we need to answer how large the V2 in here. So this is our purpose. So we may keep the V2 on the right hand side, and then move all of the parameter to the left hand side. And then we know that the condition 1, we can remove the P1. And then we have two second conditions. Oh, sorry. And then we know that the P2 in here also exposed on the air. So the P2 will also equal to the 0. OK， 我先盯住它，等下下课来换换看。怎么了？哦，那你赶快试。然后先锁门，哎，对 ，good， 好。Okay, so and then P2 also the it's posed on the air, right? So the P2 also gauge there's no gauge pressure, and then so we also remove the P2. Okay, and then we know that for these questions we assume the V1 我不能乱动它，太可怕了。The V1, OK， 大家先把问题都抄起来，随时我们会没有荧幕。So we have the V1, and then because the V1 is the liquid surface, and when the water flow out on the port 2, so the liquid surface also going down, right? But we assume the V1 is quite smaller than the V2. Because the V2 is a small hole, so the water flow out can be, velocity is higher than the water surface decrease. Okay? So in that case, we may ignore the V1 is quite smaller than the V2. So we reorganize the equation in here is the, as I mentioned, we just put all of the parameter to the left-hand side, and this is a gamma D1 minus the D2, okay? And we move the V1 to the right-hand side. So we have the V2 square minus the V1 square, right? And as I mentioned, the V1 is quite smaller than V2. So we still can ignore the V1 item in here. So finally we know that the V2 square should be equal to 2 times gamma D1 minus the D2, and divided the density, right? So the V2, how large the V2? The V2 is the root 2 times gamma and the D1 minus D2, and divided the rho. And then we know that the gamma is a low g. Gamma is low g. So we can cancel out the rho. And then the final equation is the 2g and the D1 minus the D2, right? Because the gamma is equal to rho g, so we can cancel out the density. Okay, so in that case, you can put all of the number you know in the equations. So the V2 is equal to the root and the 2 times 9.81 meter per second square. And the D1, D2, we actually know is 10 meter in here. So we have a 10 meter. And then use your calculator to compute the final answer. And take a root. So it's around 14 meter per second. Okay, so this is a very simple idea. If you have the liquid on the tank, and you create the hole on the buttons, and you can compute how fast velocity flow at the port. Okay, so this is our very simple exercise to apply the Bernoulli equations. Okay, and then the second exercise for the Bernoulli is quite important. This is safety height, and in here we call that the helmet. Okay, we call it helmet. So, and what's the problem for this exercise? We would like to understand the ventilations of the helmet. What is the ventilations? The ventilation is the 通风 我们戴安全帽不是很紧吗？其实很热，所以安全帽上面都会有一些 hole， 那就是要让它去通风的。那我们怎么知道这个安全帽通不通风 ？OK， so the key knowledge is that we need to estimate the ventilation behavior. So what's the problems? As you can see, you have the point A in here, and another is the point B in here. So the idea, if we have the pressures, and the pressure in here is the PA, and the pressure here is the PB. So we can understand the pressure difference should be the PA plus the PB. So the ventilation behavior, if the delta P is large, that indicates the ventilation behavior is good. If the delta P is small, so the helmet design is not quite good because the ventilation is poor. OK， 所以 delta P 越大就代表越通风，所以我们要去算 delta P 有多大。OK， so the idea is how large pressure difference between the A and B. So we pick out the two points. The point in here, the 1, and the point 2, and then we have the point 3 and the point 4. Okay, so totally we have the 4 points. So we can apply the Bernoulli equation to do the balance. So how can we do the Bernoulli balance? So you have a 2 point on the string line is the point 1 to point 2, located at the same string line, right? And the point 3 and the point 4 located at the same string line. So you can individually apply the Bernoulli equation for the 1 to 2 and the 3 to 4. And how the pressure difference, you need to compute the pressure difference, the P2 and the P4. Okay, so you need to compute the key knowledge in here. We need to understand how large the P2 and how large the P4. And the pressure difference between the point 2 and the point 4 is our purpose. It's our purpose for these questions. So we need to compute the pressure difference. Okay? 我又太冲动了，去移动它。OK. 所以我等一下字会写的比较丑，因为我不能动它。Okay. So what's the idea? As I mentioned, so the 1 to 2, right? And the 1.1 to 0.2 satisfy the same string line. And the Bernoulli, apply a Bernoulli equation, we know that the P1 plus the gamma Z1 and the plus the 2 over rho V1 squared is equal to the P2 plus the gamma Z2 and the plus the 2 over rho V2 squared, right? And as I always emphasize, the point 2 is a stagnation point. Stagnation point, 停滞点. Okay, because the stagnation point, so we know that we don't have the V2, right? Because the V2, the point 2 is a stagnation point. So we don't have the velocity at the point 2. And then we know that the pressures at the point 1 is far away from our target. So the P1, the gauge pressure for the P1 should be equal to 0, right? Because the P1 is on the air. So we don't have the P1 gauge pressures. So based on the two conditions, so you can reorganize the equation you have. So we remove the P1 and we don't have the V2. So you can calculate how large the P2 we have. How large the P2 we have. And we know that the third condition, we actually know that the Z1 is always equal to Z2, right? Because they are under the horizontal string line. So there is no elevation difference between the V1, V2. So we can also remove the V1 and the V2 items. So we know the pressure 2 is equal to 2 over rho V1 squared. Okay? So we can compute the how large the pressure at the location 2. So 2 over 1 and the density is here is the air, right? The air, and the air density, we know that around the 1.2. The air density is the 1.2. So there is 1.2 kilograms per meter cubic. And we know that the V1 velocity is the 12. So we have the 12 square, and the unit is a meter square per second square, right? And you can compute the final pressure we have at the location 2. So 1.2 multiply the 12 square and divided the 2. So it's equal to the 6.4, and the unit is should be the newtons per meter square. And then this unit is, we call that the power, right? So it's the P2 we have, the pressure is the 86.4. So we move to the another string line. Another string line we have the 0.3 to the 0.4. Okay, so it is another string line. So we need to rewrite the Bernoulli equation again. So we have a P3 plus the gamma Z3 and plus the 2 over rho V3 squared should be equal to the P4 plus the gamma Z4 and plus the 2 over rho V4 squared. Okay, again, so we rewrite the Bernoulli equations. And then the same ideas, we don't have the P3. Okay, because P3 is the point 3 is far away from the object and exposed on the air, so the gauge pressure is equal to 0. Okay, and then we need to know our target. We need to know is how large the P4, and so we just keep the P4 on the same side. So we have all of the parameter move to the left hand side. So we have gamma and the Z3 minus the Z4. Okay, we just move the Z4 to the left hand side, and plus the 2 over rho and V3 squared minus the V4 squared, and then equal to the P4, right? So our purpose is the P4. Our purpose is the P4. So, and then in here, because the air density is we only have the 1.2 air density. 1.2 air density. And we assume because the exercise didn't tell us how the height difference between the 3 and the 0.3 and the 0.4. So in this item, we just we assume the elevation difference caused by the D3 and the D4 are quite smaller. So, will influence the pressure, but its influence is quite smaller. So we just remove the item for this D3 and the D4. 就是安全帽的那个，大家都知道安全帽的那个高差很小，就是公分级的高差。然后因为空气的密度又这么小，所以如果它再乘上空气的伽马，其实造成的压力变化非常的小。所以我们在这里可以很省略的把它忽略掉。Okay, so we just ignore the elevation difference induce the pressure variations. So we only have? We only know that the P4 will equal to the 2 over rho and the V3 squared minus the V4 squared. And we know that the density is the 1.2 and the kilograms per meter cubic. And the V3 is also the 12 in here. So we have a 12 square minus the V volt is the 18. So the 18 square. And the unit dimensional is the meter square per second square. So you can compute how large the pressure difference, how large the pressure at location 4. So the 12 square minus 18 square, okay? And multiply the 1.2 density and divided the 2. So it's equal to the minus 108 par. Okay, so right now you already know we have the different pressures, how large difference we have. So we can compute the delta P should be equal to the P2 minus the P4, right? So this is our final delta P. And the different helmet will design, when we design the helmet, and we just look the how large delta P we have. And then we will influence the price of the helmet. It's caused by the different efficiency for the ventilation. Okay, for the ventilation problems. Okay, so two exercises are quite simple ideas. Just a simple idea, and we just check the two important knowledges. The first one, you need to double check the condition flow. The flow condition is satisfy Bernoulli equation or not. Three important assumptions is the steady flow, incompressible flow, and the inviscid flow, right? And the second knowledge is you need to check the 2 points are located at the same straight line. If not located at the same straight line, you cannot apply Bernoulli equation. So the idea for here, we just separate the two straight lines. The first straight line is 1 to 2 points, and the second straight line is 3 to 4 points. So you only can apply the Bernoulli equation when you pick up the 2 points at the same straight line, and you can apply the Bernoulli equation for the 2 points. OK， 好了，是不是我们先